Everyone, good morning and welcome to the seventh installment of our 2022 webinar series. Today, Dr. Lesley Owens will be taking us through a discussion involving validation and methods. Just as an introduction, Dr. Lesley Owens is an analytical chemist with research specialties including chromium speciation, environmental sample design, elemental spectroscopy, and metal contamination in food products. Dr. Owens graduated from Emory and Henry College with a BS in chemistry and a minor in mathematics. Owens, a Cunningham Fellow, received her PhD in analytical chemistry from Virginia Tech. And now I'm going to go ahead and pass it on to Lesley. Thank you.
Today's talk will cover the purpose of method validation, the different types of validation, and the 7 characteristics shown to the right. And finally, we'll talk about how method validation activities are performed at Inorganic Ventures. So, what is validation and why is it necessary? When I'm defining the topic, I like to go to the dictionary to find the definition. And as you can see, this isn't a great definition. It still uses the term valid. So what does it mean to be valid? This means that we're well-grounded or justifiable. We can also think about validation as supporting or verifying something from a sound or authoritative basis. This demonstrates that you know what you're doing and you are the expert. We want to make sure that when we're doing validation, we're looking at the entire process. And the goal here is consistency. At Inorganic Ventures, this means looking from the manufacturing process all the way through packaging and our shipping process. For your organization, that could mean your sampling technique and sample preparation and so forth. The goal that we are trying to achieve is this idea of fitness for purpose. We use the term fit for purpose a lot at Inorganic Ventures, and you'll see this throughout the presentation. So fit for purpose also means that it's appropriate for the intended use. So product validations at Inorganic Ventures ask 2 basic questions. And the first is the product what we say it is? And the second question is, does it do what we say it does? So we'll cover this in more detail a little later in the presentation. There are 3 types of validations. First, you can validate the identity by positively confirming that an analyte is present in the sample. This is a qualitative approach. The second type is purity. You use this approach when you need to know what else is in your sample and also provide a percentage for those extra components. So that activity would be both a qualitative and a quantitative activity. And finally, the assay component. So this is what Inorganic Ventures does when we are determining the certified value of a product. When we are certifying products, we need to be able to determine the amount of material that's in the solution, and that's a quantitative analysis. Now we can shift into the 7 characteristics of method validation, and we'll start with specificity first. This is the ability to actually detect the analyte in solution. This can get complicated when you consider your sample matrix and the presence of impurities. So ideally, you want to show consistency between multiple wavelengths or masses. Here we recommend using multiple wavelengths or masses for the mass spec users to achieve a ratio of 1 when you're comparing the results for these wavelengths. You can demonstrate specificity also by spiking your sample with the analyte of interest and then comparing that to an unspiked result. So you should be asking questions like, did the analyte intensity increase? Is the increase that you're seeing proportional? And is the recovery sufficient? So line selection or mass selection for mass spec users is critical in method development. Selection criteria include sensitivity and precision. You can also, you want to be looking at whether your window is spectrally clean. Right? This means you're free of interferences. There's no odd background going on, no weird peak shapes, and so forth. So in theory, you should use all of the lines that are available which meet the criteria above, but in practice, this generates a lot of data that needs to be handled. So the general recommendation is 2 to 3 lines or masses if possible. Okay. Specificity is qualitative in nature, and it provides information regarding impurities or interferences. You can use semi-quant methods on your instrument to help you with this part of method validation. So here's an example of how to demonstrate specificity. So this is from a special project that we did in collaboration with a customer. So the same solution here was analyzed for barium at 2 different wavelengths. Then the ratio was calculated, and we found that to be 1, which is in the acceptable ratio range as shown in the yellow and also the green. The next characteristic is linearity. So the range over which you get a signal is called the dynamic range, and the range where the signal is proportional is called the linear range. It's also referred to as linearity. So this is important when you have a multi-point calibration curve. In addition, properly prepared working solutions via gravimetric preparation, which we've heard about already during the conference, and also solutions that are compatible, another topic we've covered during this conference. So those aspects are going to ensure that you're minimizing sources of error in your calibration. So as you can see on this plot, the dots in the orange area shown here of the calibration curve is where the line starts to fold over. So when this happens, what you want to do is remove these points and leave only the concentrations that are in the linear or proportional range. Then you can do regression analysis to create your calibration curve as shown here. Continuing with our example from before, the line here has a correlation coefficient of 397, which is acceptable per the criteria set by the customer. We can further limit the linear range by looking at what's called just the range. So this is going to be the interval between the upper and the lower expected concentrations of the sample. Typically, this is going to be set at plus or minus 20% of your target value. So in the barium example, the expected concentration is 10 ppm. So the range here is going to be 8 to 12 ppm using the 20% specification. The correlation coefficient of this smaller portion of the curve is higher than what we saw for the entire curve. Now, this makes sense when you think about the error associated with calibration curves. So you think of the error in the calibration curve as having a bow tie shape. So there's more error at the end of the calibration curve, and there's less error in the middle. So you're likely to see higher correlation coefficients in this middle portion, or that range that we're talking about here. The next characteristic is accuracy. So this is going to be defined as the agreement between the accepted value and what you're actually measuring. It's also referred to as this concept of trueness. So best practices for this type of validation criteria will include the use of reference materials. So you're going to process a reference material just like you do a sample, and then determine if your method is returning proper results. So here you can use SRMs, so that's standard reference materials, which is a term used by NIST, or you can use CRMs, certified reference materials, and those are going to be available from commercial producers like Inorganic Ventures. A second method is acceptable if no suitable reference material exists. So you're going to have some times where you can't find an analog for what you're looking for. So at that point, a second method is something that you can use. At Inorganic Ventures, what we do is use a wet chemical assay where possible to verify the accuracy of our ICP analysis. So we're just going above and beyond what we're supposed to do just to make sure that we're getting the right number on the C of A. Other ways to satisfy this requirement would be via standard additions analysis. So here you're going to spike known quantities of the analyte into the sample. This type of analysis is really useful when your sample matrices are complex. You can basically get rid of any matrix effects by using standard additions. Also, spike recovery is a similar technique. You can use that also to demonstrate accuracy. In this example, we're performing a recovery analysis to show accuracy. So this is for a target solution of 10 ppm barium. And what we're doing is analyzing within that range, so the 8 to 12 ppm concentration range that we identified earlier. So samples here are prepared independently of your calibrators, and we do use a QC to ensure that our process is in control. So a plus or minus 5% acceptance criteria, so a recovery of 95% to 105% was met for all samples in this particular study. The next point we can talk about is precision. So here we're talking about the agreement of multiple measurements, and this is also, you can think of it in terms of the spread of your data. So think about those Gaussian curves that we talked about in the statistics section. So precision is typically going to be expressed as a standard deviation. It can be a relative standard deviation sometimes, and then other times you'll see this expressed as a confidence interval. Okay, there are 3 levels of precision. You don't have to show all 3 of these, but you should show at least one. So as with line or mass selection that we talked about earlier, more is great, but it's also more work. So this is where the fit for purpose idea can be applied. So do you have more than one lab? Do you have more than one instrument? Is there more than one technician running this? So answers to these questions will help you determine which of these levels is the most appropriate for your method validation. So as you've heard from other speakers throughout this conference, there's a number of issues that can affect your measurement, and you should look at some of these sources of error if you're experiencing problems achieving an appropriate precision. So all these tips and tricks you've been hearing this week can help you if you're experiencing precision issues. In this example, we're using the data set from before, but this time we're going to use the RSDs, and we're going to express it as a percent RSD. So the acceptance criteria here is a generous 5%, and you can see that we're well within the established specification. Next, we can talk about limits, specifically the limit of detection and the limit of quantification. So limits are going to vary from instrument to instrument and method to method. So for the limit of detection, what we're trying to assess is the smallest amount of analyte that can be distinguished from our background. In math terms, we say this is 3 times the signal to noise ratio, or sometimes it's referred to as the noise peak to peak. So for validation, you want to measure your samples near this value to ensure that you're on the right track. The same goes for the limit of quantification. Measure your samples at what you're determining to be the limit of quantification. So what is limit of quantification? That's defined as the smallest amount of analyte that can be quantified. We're not just detecting the material, but we want to actually measure the material with a high degree of certainty. Okay, for this, what we're going to do is increase the signal to noise ratio by a factor of about 3 over what we did for the LOD, or limit of detection. So here we're looking at 10 times the signal to noise ratio. I find it helpful when we're thinking about limits to think about these Gaussian curves. I think it helps explain the concept a little better. So what you're looking at here is a graph of a Gaussian curve for the blank on the left, and you've got your sample on the right, and your concentration is on the x-axis. So for the blank, there's an equal probability of being above or below the average blank signal. Okay, so you want your sample curve to be separated from the blank curve. So you don't want these on top of each other. Okay, so the area under the tail of the blank curve. So I'll get my laser pointer out here and highlight what I'm talking about. So the area under the tail of the blank here on the right side is what I want you to focus on for the remainder of this slide. So if the curves overlap, so you slide that sample over to the left, what you're going to have is a 50% probability that your sample doesn't contain the analyte of interest. All right, so that's not the best odds. Okay, so when you move that sample curve over to the right, so we're going to move it by 3 standard deviations over to the right. What happens in the tail here is you're getting a 1% area actually showing up higher than the detection limit, right? So this would be telling you that there's a 1% chance of a false positive actually occurring here. Okay, so remembering that your probability curve never touches the x-axis, or it's never 0, and think about visually moving this another 3 standard deviations to the right. So now the area under that curve in the tail that I highlighted earlier is going to be very, very small, which indicates that there's a very small chance that the value that you detect would be considered a false positive. So that's what we're going for. So 3 times is your limit of detection. You've only got a 1% chance of a false positive. You move that out to 10 times, you're looking at a very small percentage of a false positive result. And the final validation characteristic is robustness. So what we're looking at here is the ability to withstand small changes. You don't want a method that's so specific that you cannot make any modifications to this method. Modifications would include changing things such as your pump tubing, even your acid supplier, or the nebulizer that you're using. So, ideally you want the freedom to choose different options, because we all know things happen in the lab, and maybe a particular spray chamber is not available on that day. So can you substitute another one, or are you in a down situation? So paying attention to robustness when you're validating your method can actually lead to less downtime in the lab. So this is kind of the last step, but you need to spend a bit of time here to make sure that you're getting a really solid method that can withstand those small changes. In our example, what we look at here is the percent RSDs for 2 different analysis times, and we use that to demonstrate with our data that we're within the acceptance limits set by the customer. So again, percent RSD here was less than 5%, and we're well within the specified percent RSD. We're going to wrap up this presentation with validation at Inorganic Ventures. So earlier I said here at Inorganic Ventures we focus on this idea of fit for purpose. So questions like, does this method make sense in our lab, and do the results make sense? Okay, so you can apply those questions in your laboratory as well. So in our validation, what we need to think about is how our instrument will be used. Okay, so we use our ICPs to certify our single element products, and we also use our ICPs on a different method to check the custom products that we produce. So here we're just verifying the concentration is within a certain tolerance. Okay. We established linearity as part of the instrument qualification. And then for our singles process, we're validating an existing method. So we're just doing what's called a method transfer. So we're just moving it from one instrument and popping it over onto the other. For our custom products, we're essentially doing the same thing, But here, what we do is we validate we verify that the performance is the same for particular solutions on the old instrument and the new instrument. So again, a method transfer type activity, and we can demonstrate validity by doing the comparison of one instrument versus the other. Unfortunately, there's a lifetime for your method validation activities. I wish this wasn't the case, but it is. So monitoring and trending of your control samples is a really good way to determine if your method should be revalidated, as well as it'll inform you on the type of revalidation activities that need to be done. So you may only need to look at one piece, or you may need to look at the entire method. Again, this is going to be dependent on the age of the method and what, if any, changes have been made. So anytime you make a change to your process, you should really consider the impact to the method and determine if revalidation is necessary. So the extent of revalidation should be evaluated in terms of this idea of fit for purpose, and you should only reevaluate the pieces that you've identified as needing to be revalidated. Don't do more work than you need to when it comes to revalidation. In summary, the method validation process ensures the reliability of your results. So you can validate your method in concurrence with your development activities. So you don't have to do these sequentially. So, and lastly, procedural changes. So anytime you make a change to your procedure, it may warrant another validation. So make sure you're using risk assessments, looking at what's changed in order to determine if a revalidation is necessary. So be sure that you're comprehensive and you're thorough during your initial validation, and that'll also help you avoid unnecessary revalidation. So these are resources for your reference. They're in your packet, so just take a look at them on your own, and if you have any questions on the material, just let us know, an email or a phone call, and we can walk you through the finer points of these documents. So finally, I'll conclude with this slide about our technical support resources that are available on our website. So feel free to send us an email or give us a call if you need assistance with your analysis. So thank you for your attention. And remember, if you have any questions, to submit them in the chat, and we'll answer them during today's roundtable.
All right, Lesley, thank you for that informative presentation. And now we're going to move into the Q&A session for this presentation. So Lesley, thanks again. So we'll jump right in. The first question, do I have to follow this approach to validate every method every time?
No, the answer is no, you do not. So this is going to be the basic framework for validating a method, but you don't have to follow it strictly every time you validate or need to verify something. Something like a method transfer verification would use different pieces of the framework than validating a new method, for example. Some methods may not need the full validation. So, when your value is just informational or you're not being audited on any of this material, you wouldn't need to be extremely rigorous when you're looking at your method. Also, if you're just running a quick analysis for maybe a ballpark estimation, you don't need to do any validation. Maybe. However, you still need to be aware of the potential sources of error or problems in your method. And like we say for standards, your method needs to be fit for purpose.
Cool, thank you. A question from Paulo is looking for access to the slides. I know we make these videos available on our website. I believe we make them available in PDF? I think I may have done it before at some point for a presentation years ago.
We do, James. Yep. PDF will be on the same technical videos page on our website. You can check out the recording and then download the slides right there.
Splendid. All right. So Paul, yeah, they'll be able to access those. Yeah, like Maddie just said. Okay. How is acceptance criteria defined? This one's from Adnan.
Sometimes it's defined within the method itself. Other times you have to define the criteria. So if you're having to define your criteria, you would have to make it reasonable based on what your lab is capable of doing. And, that involves your instrument that's taking into account error budgets for everything involved in your method. And that's a little more complicated. It's easier if it's just given to you. So if you have any questions about that, we can walk through kind of reasonable acceptance criteria offline.
Good, awesome. All right, this next question actually comes from Gary. How much validation is actually done using real world samples, i.e. spiking real world matrix with IV standards?
Yeah, it's ideal to either find a reference material, or if you can't do that, you can spike the reference material, as you mentioned. I recommend that you do that every time you validate your method. That's just going to give you the peace of mind and the check that what you're actually trying to measure is coming back correctly. As far as actual percentages out in industry, I'm not sure about that, but the recommendation would be to do that every time if possible.
Good. Okay. Let's see. What if I can't find a real world reference material?
Yeah, that's a really good question. So, finding a reference material that exactly matches your sample can be pretty difficult. NIST has a library. There are other reference material producers that are more on the real world type sample track, but sometimes you just won't be able to find exactly what you're looking for. So, we recommend finding something similar. If you can find that similar analog, then go that direction. And if not possible, you can use a CRM and analyze that like a sample. So a solution from Inorganic Ventures, for example. There are limitations to this approach. For example, what you would do here would be running your CRM like it's your sample. So you run it through the exact same sample prep, but the problem could come up where your sample is a solid and you wouldn't be able to fully assess the dissolution or the digestion that you're trying to do for your sample. So there are some limitations on that. You can run a second method as verification on your sample, or you can do some other things that I mentioned in one of the slides earlier. So second method or spike recovery, for example.
Okay, awesome. Our next question is from the chat coming from Pintu. Hopefully I'm saying that right. Is there an SOP for cleaning validation using cleaners for lab instruments?
I am not aware of one. Depending on your industry, there may be one. I know USP has some different methods for cleaning materials. I'm not 100% sure what those numbers would be for those methods. They may be out there. As far as a universal SOP, I'm not aware of one of those either.
Okay, and I was just looking around on our website through the videos to see if we had just kind of like a general maintenance guide. I know we've got some, we talk about washout in some of these, but I'm looking for one. If we can find a general one of our ones on general maintenance, we'll get it sent to you. We'll push that along to you just so you can have at least a starting point. Okay. All right, so next question. What if I change my sample matrix? Do I have to revalidate?
Maybe. It really depends on what the change is and how significant that change would be. Also, was this change accounted for when you were looking at the robustness of the method? You may not need full validation if you included this type of matrix when you were assessing robustness. We all know that not every sample is going to be in the same matrix. So when you were doing your robustness testing, if you accounted for this matrix, then you wouldn't have to make the revalidation. for that particular change. If the change you make will cause a known issue, an interference, for example, maybe you've got chloride coming in and you know the chloride from your matrix will cause an interference, or maybe you have silver in your system, maybe that precipitates, you would need to do a little more to show that that change has not affected the overall method. So this is one of the reasons why taking your time in the robustness phase is really important.
Good. Okay. Good. We've got a few more still rolling in here. This next question from Adnan is referring to, it looks like it's referring to using the quadratic equation for validation instead of maybe like a linear equation. Do you have any thoughts on that?
Yes, I do have thoughts on that. So I am very much a purist when it comes to calibration. So, you know, y equals mx plus b is more of where I would prefer to see calibration performed. The issue is, you know, you start getting situations where you don't have one unique concentration for every signal intensity that comes in. A lot of instrument manufacturers will allow higher order calibration, so quadratics, for example, you know, polynomial type expressions. Just proceed with caution and make sure you absolutely understand what is going on in that calibration so that you can thoroughly explain that to an auditor and defend the answer that's coming out of your instrument.
Good. Okay. Thank you. This next question, can you talk about the differences in minimum validation requirements for analysis in different phases of clinical trials?
So that is a very specific question, and unfortunately, I don't have experience with you know, the different validation in clinical trials. I'd be happy to have a discussion on what's presented with the method, but I would need to read that method before we have a discussion. So if you'd like to send us an email, we could set up a time to go over that information, and I'd be happy to walk you through what I see in that literature.
Makes sense. All right. We've got another one here from Gary. Does IV have any plans to create a range of spiked real-world matrix standards like metals in typical wastewater drinking water? He's guessing the stability may be an issue in some instances, or could a synthetic matrix be considered?
Right. So this is something that we're always considering is, you know, the availability of real world samples is limited in some cases. And, you know, you have some very common real world type samples like wastewater, as you mentioned, Gary. So yeah, it's something that we think about, but it's not been something that we've actually pursued yet. I'd be happy to pass this along to Mike in the R&D department and see where they think we could go with something like this.
All right. I think we've come to the end of our line of, or our list of questions here. So I'll take this last one from Alexander. Can I validate through aptitude tests only?
I'm not sure what you mean by aptitude tests.
Yeah, we may want to get Alexander to follow up with Lesley or our technical staff to kind of maybe elaborate on that.
Yeah, if you could just send us a little bit more detail on that, info@inorganicventures.com.
Right. And in typical fashion, as soon as I mentioned something about the last question, we get a couple more, but that's fine. Adnan is asking about in linear calibration, we always have y-intercept and give variation on low concentration, or looks like they're getting variation on low concentrations. When we force it to pass through zero, how does it impact the validation?
Right. There are certain situations where you would want to force through zero and others where you would not. I answered this question as part of the Q&A on in our ICP conference. It's a fairly involved answer, and I do have it all typed up that I sent to one of our participants. So if James will pass along your name, and I can get that info over to you. So there's considerations that you would need to take for forcing through 0 versus not.
Fair enough. Okay. All right, and with that, I believe we've come to the end of the questions, so I'm going to go ahead and wrap it up there. Thank you, everybody, and thank you, especially Lesley, for your presentation. And if I'm not mistaken, this wraps up our 2022 webinar series for our Be Bold series. So thank you, everyone who's been participating, and we wish you a good day and good holidays. Thank you, everybody.